Hello. Here's a quick demonstration of deriving the Poisson distribution from the binomial, because that's where we start. Okay. Um, Quick reminder that we use the Poisson distribution quite often to deal with queues, either people ringing up for phone calls or shops. So it's the people who ring up and their rate of arrival. We also in engineering use it for equipment failures and frequency. And the important thing here is that the probability of success in each of the trials, current probability, is very low, and there are a very large number of trials, and usually these trials are effectively small periods of time, so a minute or a second or a millisecond if you're working on the internet and you're getting thousands of hits on your website. So the example I used in my explanation of the Poisson was that we had a bank, and a bank's getting 120 customers arriving on average every hour. And we looked at what the probability was then that we got 3 customers arriving. But the important thing here is looking at arrival rate and the probabilities. So in what we've just seen above, well, 120 customers arrive in an hour, so that's 2 customers per minute, and we're going to call that lambda. That's our 2 customers per minute. And what we looked at doing in the previous example was chopping up the period into smaller and smaller slots. So if we start with our minute and we chop it into 10-second slots, we'd have 6 slots. And the probability of a customer arriving in every 10 seconds, well, we're expecting 2 customers a minute, but actually each of these 10-second slots is only 10 seconds out of 60. That's 1/6 of the time period, so we'd expect only 2/6 of a person to arrive in each slot. That would turn into 1/3, wouldn't it? So we'd be looking at a binomial with n trials and probability of 1/3 on each trial. So here we're starting to see our p getting smaller. If I looked at extending that by using a table here, if we have 10-second slots, there are 6 of them, so that's 6 trials, and the probability on each one is 2 out of 6. If we then went down to 1-second slots, we'd have 60 slots or trials, and the probability of success in each one will be 2 out of 60. And if we went down to 1/10 of a second, we'd have 600 slots, trials, and the probability of success in each trial would be 2 out of 600. What's important about each of these is if we take our NP values for each of these, it remains constant at our value lambda. And that's what we're going to use as we make our time periods, our slots. These are, and therefore our n, getting larger and larger, and n's going to start tending to infinity. Okay, so what's the probability of success of our successes or our arrivals? Well, we know that from a binomial is that probability therefore is n choose r over p to the r q to the n minus r. What happens then as n tends to infinity in a binomial distribution where we've said that we've got our n is our number of trials and n's going to infinity, and our probability we looked at earlier is effectively lambda over n, and n's tending to infinity. So if we just grab hold of our standard equation, here's our n choose r is n factorial over n minus r factorial r factorial. There's our p to the r and q to the n minus r. If we now sub in these 2 values, that p is our lambda over n and q is 1 minus lambda over n, we get this form of equation, this form of expression for it. So I've written out my n choose r now in this form. So I've got n, as if you had written it out to calculate it by hand, you're going to have n times n minus 1 times n minus 2 all the way down to n minus r plus 1. And on the bottom we'd have 1 divided by 1 divided by 2 divided by 3 all the way up to r. So what you can see here is we've got r factorial here on the bottom, haven't we? That's r factorial. here's our first bracket, probability bracket. That's lambda over n to the power r, which of course we can convert here. We can open that bracket up and we can just write it as lambda to the power r over n to the power r. And this is going to be very helpful when we look at our r factorial here, because what we're going to do in our next step is just swap their position. So that r factorial is going to go below our lambda, and look, here's the first term that we want, isn't it, for our Poisson, lambda to the power r over r factorial. That's what we want. We're going to have to swap over then the n to the power r over here. Now if we actually count along here, we've got 1, 2, 3 all the way along here. We've got r terms here, 1, 2, 3, 4 all along, and on the bottom we had n to the r, so we can put an n underneath each of these terms, the top terms and the numerator, and we can therefore make pairs here all the way along, isn't it? Well, n over n obviously equals 1, doesn't it? But as n tends to infinity, we can see that n minus 1 over n is also going to tend to 1, and n minus 2 over n is also going to tend to 1, and all the way down, because r is quite small compared to n, so this final term, n minus r plus 1 over n, is also going to tend to 1. So what have we got? We've got 1 times 1 times, as n tends to infinity, we've got 1 times 1 times 1 times 1 times 1 all the way along here, which of course is 1 to the power r, and 1 to the power r is 1. So that made our life easy, because effectively that term, that part of the expression, is just going to turn into 1. We've already identified that this term we want, and that's in our Poisson, and that just leaves this one over here on the end for us to play with. So let's have a look and see what we can do with this term to simplify it. There we are. Okay, well, that's n minus, the power on this is n minus r. So we can rewrite that and leave our 1 minus lambda to the n on the top, and then we can divide it by 1 minus lambda to the over n to the power r. So what's going to happen to these terms? This one's a tricky as n tends to infinity. We'll come back to the top one, but what happens to this bottom term here? Well, that n is going to go to infinity. So this term here is going to therefore tend to 0. It's going to tend to 0. So on the bottom we're going to have 1 to the power r, which is going to be 1. So effectively that term's going to disappear, isn't it? It's just going to become 1. So on the next line down here we can see that we've now got our lambda to the r over r factorial, which is what we wanted, and we've got a 1 minus lambda to the power n. How are we going to deal with this term here? Well, we are going to use Maclaurin. So if we use look at a Maclaurin for expanding 1 plus x to the n, we're going to find that it's 1 plus nx plus n minus 1, there's our coefficient, times x squared, and then n minus 1, n minus 2 over 1 times 2 times 3, so that's 3 factorial x cubed, yeah? So if we just sub in for x r minus lambda over n that we've got in our expression here, then we can see what our pattern now looks like. If we expand those brackets in the first term here, so we've got our 1, then we've got our n here, we've got in this term here, we've got an n on the bottom, n on the top, so that cancels out, and so there's our minus lambda. Now, using the trick we used before, we can move that 1 over 2 and put it in the third term here. We can move that effectively under the lambda squared, so there's that term, and we've got an n squared on the bottom here, so we can put that again, break it up, and we can create n over n. Here we've got an n over n there, and here we've got an n minus 1 over n. And what's going to happen to that? Well, we know once again that as n tends to infinity, this lot's going to tend to 1. Yeah, that lot's going to tend to 1, isn't it? If we do the same trick here on the lambda cubed, and we've moved this, which is a 3 factorial underneath it, again we've got an n cubed on the base. So breaking that up, we can put these into little fraction pairs. So we've got n over n there, n minus 1 over n there, etc. So each one, n minus 2 over n there, and each one of those tends to 1, so that tends to 1 as n tends to infinity. So that simplifies our world in that we end up with 1 minus lambda plus a half lambda squared minus 1 minus 1 over 3 factorial lambda cubed plus 1 over 4 factorial lambda to the 4. Now, those of you who've done a lot of C1, C2, C3, 4 will know that that is the Maclaurin expansion of e to the minus a lambda. And that's what we were looking for, wasn't it? So therefore, we've reached our conclusion. That this is lambda to the power r factorial over e to the minus lambda. And what we've effectively proved to ourselves is that if we take this binomial with n equals, so the n value is n, but the p value is lambda over n, and then we let n tend to infinity, then our binomial probability is going to tend to lambda to the r, e to the minus lambda, r shriek, which is factorial, which is what we're looking for, isn't it, in a Poisson distribution. So there we are. That's how we get the equation, the probabilities for a Poisson distribution. I hope that's of you.